Yes.
Thanks. Yeah. Okay. So last time we started the classification of semi-simple Lie algebras. Actually, what we are rather considering is a simple Lie algebra, and then the semi-simple ones, which are direct sums of simple Lie algebras, can be made up of decompositions of the simple Lie algebras. And furthermore, we are only studying the simple Lie algebras in 2 dimensions. So the algebra is two-dimensional in the sense that the Cartan subalgebra has 2 simultaneously commuting operators. And there may be a bunch of other operators, such that the rank of the group is m. So the rank is the number of simultaneously commuting operators. I think that came out quite confusing. Okay, so as an example, we had for SU2 only one commuting operator, and that was J3. J1, J2 did not commute with J3. Instead, actually, we combined J1 and J2 to create the step operators. For SU3, we have 2 simultaneously commuting operators, so T3 or T8 equals to Y, and the others would correspond to the other generators. And what we did last time was that we started to require the property of a step operator. So we wanted to construct a linear combination of generators, which EA, which are not in the Cartan subalgebra. So we want to take some linear combination of those with the property that that linear combination is an eigenvector of the action given by the commutator of the element HI, which is an element in the Cartan subalgebra. So we want HI commuted with the linear combination is a constant lambda eigenvalue lambda times the linear combination. So this has the form of a commutator here, but it is a linear operator, so we can view it as a matrix if we want. And then what we did was that we wrote down some constraints on that matrix if we saw it as a matrix. And we wanted then to find the eigenvalues lambda of this operation seen as a matrix, and those eigenvalues can be found by requiring that the determinant should vanish. So we had this condition where this C was constructed in this way up here. And I just came to the fundamental theorem of Cartan, which says that the eigenvalues alpha I of a given HI are non-degenerate. That is, there is only one eigenvector, E alpha I, corresponding to each eigenvalue E alpha I. So the eigenvectors can be labeled by their eigenvalues, hence E alpha I. So we have then HI commuted with E alpha I is alpha I E alpha I. Again, this is a case where the proof of the theorem is beyond the scope of the course. So I rather give some overview of what exists than digging into this or that detail. Okay, so now we assume that we have an eigenvalue E alpha I of HI, eigenvalue in this eigenvector in this commutator sense. And we want to consider some other HJ, some other element in the Cartan subalgebra, which is not equal to HI. So to study the effect of HI Hj effect that is in this commutator sense on the eigenvector E alpha I being an eigenvector to Hi, we take this double commutator. Why? We will soon see. So we study Hi commuted with the commutator Hj E alpha I. So we study the effect of Hi on this state here. Then we use the Jacobi identity, which is trivially fulfilled for matrices and is a constraint on the algebra. The Jacobi identity says that if we add up cyclic permutations of the objects here in the brackets, we get 0. So we do that with the add up cyclic permutations, but we move the other two permutations to the other sign, so they acquire a minus sign each. So let's have a look. Here we have Ij alpha, and then I should stand on the other places as well. So we have here, for example, Ij alpha, so that's a cyclic permutation, and Ij alpha, that is the other cyclic permutation. Now, if we look at this expression here, the commutator between Hi and Hj, they are in the Cartan subalgebra, so they commute with each other. So this commutator is 0. We have constructed E alpha in such a way that E alpha commuted with Hi should be alpha I E alpha I, and to be picky, there should be little bars over the alphas here. So this implies that this alpha I we pull out here with two minus signs. So we see that what we get is that this state here is an eigenstate of this operator here with the eigenvalue alpha I from here. Or, in other words, this, here it is an eigenvector of Hi. And using the fundamental theorem of Cartan, there is only one eigenvector corresponding to the eigenvalue alpha I. So that must be that eigenvector. It must at least be proportional to E alpha I. Sorry, actually there should not yet be bars over the alphas. My mistake. We will, okay. So, but we will just come back to that. So this implies that Hj acting on E alpha I is alpha j E alpha I. So we have required E. We have required this. We required this for a certain Hi, and we had the same relation for another Hj, only with some other eigenvalue alpha j. And now I can then label my E alphas with E subscript vector. So I'm going to combine both the I and the j into a vector, and I have some E subscript alpha vector. And of course, there was nothing special with the Cartan element that I called beta. So I can do this once for each element in the Cartan subalgebra. So my vector then of eigenvalues will have as many elements as the rank of the algebra. And these objects here are called root vectors, and the corresponding E alphas are called step operators. So recall here that this is exactly the kind of relation that we had for SU2. But with L plus, L minus, and LZ. Okay. So now we have learned the action. We know that the h with the h commutes. We know the action in the commutator sense of the h on the E alpha. What remains to be explored is the commutator of E alpha and E beta for some beta not equal to alpha. So we consider then the action of hi on this state, and we apply again the Jacobi identity. So we should have all cyclic orders here on the other side. So, and the order is I alpha beta. So I alpha beta minus sign since I moved them to the other side. And then I use here that the commutator of E beta with hi is beta I E beta. So it's an eigenstate. The commutator of E alpha with hi is alpha I because that was an eigenstate. So I have here essentially the commutator of E alpha with E beta and the one with E beta with E alpha. Well, they only differ by a sign. And to compare to the left side, I want to have the E alpha standing first. So I write them with E alpha standing first. So in this order, and I have from minus beta I, then I have beta I, E alpha commutated with E beta, and here I have alpha I, one minus sign from here, one minus sign also from the order of this one and this one. So I have also E alpha, E beta. So I am back at an eigen vector relation. So I have here E alpha commutated with E beta, and here I have E alpha commutated with E beta. Okay, so this relation was told because it comes from the Jacobi identity, which is a requirement on the algebra. And from it, we conclude that either this thing is itself a root with, so it's a root vector with this these eigen vectors. Sorry, eigenvectors of eigenvalues. Vectors of eigenvalues. So for each hi, we have beta I plus alpha I. So we can form out of those the vectors alpha plus beta. So it is then one of the root vectors, but of course it can. We have some proportionality constant, and the commutator of E alpha commutated with E beta, we take that to be some n alpha beta, and then E alpha plus beta. So that was one option. Another way of fulfilling this equality is if this is 0, then it's trivially fulfilled. And the third option is that this is 0 for all the i's. So alpha plus beta is 0. So beta is then minus alpha. So I then have the commutator of E alpha and E minus alpha. And this linear combination then commutes with all the hi's. So it is then itself an element of the Cartan subalgebra. And here we can compare to SQ2. We had some J plus and some J minus, that was 2J3. So commutator of step operator was something in the Cartan subalgebra. So it's the same pattern that we see here. Then I also like to remark that if we have Hermitian generators in the physicist convention, which we often do, then we have the E dagger of the label vector alpha is E minus vector alpha. So that is fairly easy to prove. To prove it, I take this relation and I take the dagger of it. So daggering this side, so I just write the side out and I take the dagger of it. Here it's only a dagger up there. Then dagger of this is the E alpha dagger, in principle HI dagger, but they were Hermitian. So we have this. Nothing happened on the other side, and this is now the commutator of, this is minus the commutator of HI with E alpha. And then I move the minus sign to the other side. So I have the commutator is minus alpha I, and here I have E alpha dagger. That is, I have concluded that this E alpha, Hermitian conjugate of E alpha is E minus alpha. Okay, and here I collect results that we have learned so far. So we had HI and HJ commuted because they are in the Catan subalgebra. I had that HI and E alpha was alpha I H alpha, so that I required from the E's because I wanted them to be step operators, so from the E alphas. If I take the commutator between E alpha and E minus alpha, then I have alpha I H I. So I have something in the Catan subalgebra, and if I take the commutator of E vector alpha with E vector beta, then I had some normalization constant times E with the E labeled alpha plus beta because it was an eigenvector with that eigenvalue. Then we also have for the scalar products or the killing forms that the scalar product, so there was that trace in the adjoint representation of HI with HJ is 0, so we chose them to be orthogonal. We have actually that HI commuted with E alpha that I should come back to down here, and we have seen that E alpha commuted with E minus alpha. Sorry. I'm misreading my brackets here. This is of course the scalar product. Yeah, sorry, I got confused there. It looks very similar. So. Okay, sorry, this is the scalar product. They are orthogonal. This scalar product is 0, and that is proven down here. So let's get back to that. The scalar product of these we can choose, and we choose it to be 1. So this is some normalization. And then we have E alpha commuted with, not commuted, scalar product with E beta. And this we have seen was 0 that we saw a bit further back up. So now let's get back to this second identity. So we take HI scalar product E alpha. Now, to see that this is 0, we use the cyclicity of the trace. So the trace of HJ E alpha times HI, this is then by the trace being cyclic, HJ HI E alpha, but the commutator of HJ and HI is 0 because they are both in the Catan subalgebra, so this is 0. And this thing here is proportional to E alpha with some non-zero proportionality constant. So that implies that this scalar product between E alpha and HI must be 0. So E alpha is orthogonal to HI, and that is what we had up here. So now that is also proven, and the other ones we had from before. So we have a set of relations for the Killing form / scalar product, and a set of relations for the commutators. And if you're not convinced by the cyclicness here, just try writing it out, and you will immediately see because the trace is cyclically only the relative order between the matters, and you can see soon that we have here, for example, J alpha I, and here we have J I alpha. This actually looks like there's a typo here. Is that the case? So let's see then. H J E alpha H I minus E alpha H J H I, and on this side we would have H J H I E alpha minus H I H J E alpha. And now we should everywhere have the trace over these guys. And let's see, of course it should be cyclic, so we can move things around. So we can move one term to the other side. So we can take this guy and move it to this side, and then we would have then we would have we would then have I E alpha J, but here we up here we have this thing. So I think there is a typo here. I should double check it, but I think there is a typo here. It doesn't matter because the thing is 0 anyway. So the point is that in the Killing form sense, so scalar product given by trace, and this guy is orthogonal to that guy. Okay. So so let's see if we have questions to this. Then we move on to the quantization of these roots. Because what we want to do now is that we want to find constraints on the roots, which will tell us how to quantize the possible states that we had for SU2 along a line, and for SU3 we had a two-dimensional point lattice of possible states. So in general, for a two-dimensional algebra, we have some sort of point lattice of possible states. There's possible weights to the Cartan generators, and we will find that there's only a certain fairly small number of possibilities. Okay. So first I remind you that each root is some m-dimensional vector. So the roots are these eigenvalues with components alpha j. So we can define a scalar product in an ordinary sense between the roots alpha and beta. And we can also take alpha dot h and define that to be alpha I h I. Okay. Furthermore, I define some rescaled version of this guy. So this thing is this thing rescale. And why do I rescale it? Well, it's not so interesting. It's to compare to known equations. Okay, then in terms of this that new object H alpha, we can compute H alpha commuted with E beta. One of the relations above was Hi commuted with E beta was beta I E beta. My H alpha is a linear combination from here and here of my HI's. So everywhere I have this factor 2 over alpha squared. Then I have a component alpha I for my ith element here, and that commuted with beta gave me beta I E beta. So I end up having some alpha I beta I, that is alpha dot beta. So I end up with this commutative relation. Then, as a special case of this, I can take H alpha with E plus minus alpha. And I have then here plus minus alpha squared or alpha squared cancels, of course, so I have 2E plus minus alpha. So this thing came from just here. Then I have for my E alpha with my E minus alpha that this is alpha I HI, so or in other words alpha dot H, or inserting or rewriting my H in terms of my H alpha. I see that I have the inverse of this factor here, so I have alpha squared over 2 and then H alpha. And that's the form that I want to have. And now I want to compare this to known stuff. So I introduce yet a new operator. I call it J3 hat. Why it's called J3? Well, I think you can almost guess that, and I insert a little hat on top of it to make it clear that I'm not stealing the J3 from somewhere else. I'm defining it here. So could have written like this, the definition equal to, and like this. So I define my J3 hat to be half of this H alpha from up here. And I also define hatted J plus and J minus to be a rescale version of E alpha plus minus. And using this, I rewrite my second relation above. So I have this guy going in here. So I have my H alpha. So this here is my H alpha. Here I have E plus minus alpha, E plus minus alpha. I solve from this here. So I just take the inverse of this factor. It goes here, and then I have my J hat plus minus. And now when I look at this, I see that I have the same factor here and here, so I can clearly cross it out. So I have the J3 with J plus minus is j plus minus, and that we can compare to what we have seen before, that L phi with L plus minus is plus minus L plus minus. So I obtain a relation of the same form. So that is for one of my root vectors. I have obtained a set of commutation relations that is similar to what I had for SU2. Now, taking the third relation from up here, so I take this guy. So I have my E alpha, but expressed in terms of j instead, and another E minus alpha expressed in terms of j. Then I had here alpha over 2, and I have that it should be my H alpha, but my H alpha is 2j3. So I have this relation. So I obtain this commutator relation, again very reminiscent of what I had for the commutator of the SU2 algebra. So from this we have seen that j hat plus minus, as suggested by the notation, are step operators. So they raise or lower in units of 2. So if I take what I had for SU2 and rescale, I have that this j phi hat is quantized in units of 1. But the point is that essentially we have an SU2 algebra. Actually, that is perhaps not a complete surprise if one starts out thinking about this as something that came from matrices, because if we looked at the matrix structures of things, we could think about it as if we had sigma spread out over different matrices, over bigger matrices. So maybe it's not a complete surprise that we recover something SU2 like here. Okay. So now let's see if we had questions first. Okay, so now we consider the action of one of the other step operators, say E beta on my H alpha. And then from the first, from one of the commutation relations above, from this commutation relation we had above, we see that since we must also have a quantized spectrum of points for E beta, this must also be an integer. So this is an integer. And doing this for different alphas and beta, we see that if I multiply together these, so this is alpha dot beta times so alpha dot beta I have up here over alpha squared. Of course, there's nothing special with the state I call alpha or the state I call beta, so it could be any two states and they could reverse their roles. So I can study this guy and the state with alpha and beta reversed. So here reverse the role of alpha and beta, so it's alpha squared there, and then here it's beta squared. Now if I look at this, I see that I have a factor of 2 times 2, that is 4, but otherwise this is nothing but the scalar product of alpha dot beta squared over alpha squared beta squared. So this is essentially a measure of the angle between alpha and beta. So since this should be smaller than 4, those integers n1 and n2 are severely restricted. And I can then define an angle between the alpha and the beta vector. So I take alpha dot beta over alpha absolute value, beta absolute value. So this is then 1/2 and 1 and 1 and 2 to the power of 1/2 that can be seen from up here. So the 1/2 compensates for the 2, and otherwise it's the scalar product twice, so to the power of 2 compensated for by the 1/2 here. Okay, so this means that the angle between those root vectors must be this, where each of the n1 and the n2 cannot be larger than, sorry, can be at most 4. So that means that we have a limited set of options. At first it may seem like if theta equal to 0 is a valid option, so they would then be parallel, but that turns out not to work by a not so lengthy argument that you can look up in Jones. So instead, the valid options are that both n1 and n2 are 0. If n1 and n2 are 0, that corresponds to the root vectors being orthogonal, and in this case there is also no restriction in their relative length. Another option is that n1 and n2 are both equal to 1. If this is the case, we can go and see what value we have for cos theta up here. So then we have 1/2, and we have 1 times 1 to the power 1/2. So we have a half. That is fulfilled by the angle being 60 degrees. We also have a constraint on the length of beta relative to the length of alpha. And to see where that constraint comes from, I go up here and I take n1 divided by n2. So up here I have my n1 that's copy pasted from here, and here I have my n2 from here. So of course here most stuff cancels, dot alpha to alpha dot beta cancel, and what remains is beta squared from 1 over 1 over here, and alpha squared from 1 over. So there. So I have then that n1 over n2 is beta squared over alpha squared. So if n1 and n2 are equal, then the lengths alpha and beta are also equal. So length of beta is length of alpha. Another option is n1 is 2 and n2 is 1. Then I have from this length here 1/2 root times root 2, so I have 1 over root 2, so my angle is 45 degrees. So these vectors will give it an angle of 45 degrees, and beta will be a factor root 2 longer than alpha. Or I can have that n1 is 3 and n2 is 1, then I have a different value for cos theta, so I have a root 3 from up here and the factor 1/2 from there. So I have the theta is 30 degrees, and my beta must be root 3 times alpha. So with this, if we place the root vector alpha horizontally like this, we can draw the relative position of the root vector beta. So here, for example, in the first case, beta was orthogonal. In the second case, the angle between them was 60 degrees and they were equally long. So I have something like this, etc. And here we have that done. So here I had my first case of vectors where we had no relative length constraints, but they were supposed to be orthogonal. And actually, so here we have just 2 copies of the SU2 algebra without relative constraints on them. Or we had 60 degrees between them and equal length, and that is maybe something that looks familiar because this is the algebra of SU3 that we have encountered before. Then we could have an angle of 45 degrees and a length 1 and root 2. After extending to all possible roots then, so by mirroring and taking combinations, we have this root system, which happens to correspond to the group SO5. Then we have the most complicated diagram here. So this was the case where the angle between them was 30 degrees from up here, and one was root 3 longer than the other one. And constructing the whole root system, we get then this. But this is it. This is what we have for 2-dimensional root systems. And if we had more dimensions, we have for each a pair of dimensions these sort of constraints. So one can play the same game, and one can extend this to more dimensions, and one can actually classify all the possible Lie algebras in this way and find that there are not so many. And if you're curious, you can read it in the book by Jones, but we don't have time to go through it now. This is also a very good point to take the break. So let's see if we have questions to this. Okay, then let's take the break, and I will be in front of the computer for a few minutes in between. So hello and welcome back. It would be nice to see if someone actually is back. Thanks. Okay, so what we have done during the first half of the lecture is that we have found all possible arrangements of two-dimensional algebras, and one can extend that and find all possible Lie algebras in this way. But we will not do that. Instead, we'll go back and have a look at what we did before. So we had a look at, we'll go back to the SU3 algebra. So I believe this should be more comprehensible than the first part of the lecture. For SU3, we had a
screen share.
Thanks. So for SU3, we had three-dimensional generators, and we had states V1, V2, and V3. We could say that they correspond to color red, green, and blue if we think about QCD. These states are eigenstates of the diagonal generators, so the Cartan generators, the simultaneously commuting generators. And we had for SU3 two of them, so we take H1 to be T3, and it was this thing, so essentially a sigma matrix here, sigma 3. And we take H2 to be orthogonal to this guy and diagonal, and that gives us this form here. And now it's very easy to see that these vectors are eigenvectors of these diagonal operators with eigenvalues, for example, 1/2 coming from here. And so that was H1 and V1, then we can take H2 and V2, and then we pick up just this diagonal element. And then H1 and V3 gives us 0, similarly H2, so this guy over here on V1 gives us this factor here, H2 and V2 gives us that factor, and H2 on the last V3 gives us this factor down here. So we have found the eigenvalues of the elements in the Cartan subalgebra. These are not the root vectors. So we can draw them in a lattice as is done here, but they are not the root vectors. The root vectors are instead given by the step operator. So the root vectors will take us between these states. So let's come back to that, but first I'll just remark that now we have drawn those states here, and let's see then what we have. So for example, we can take a look at the first state here. The eigenvalue of this first state should be 1/2 projected onto the H1 axis, so it should be at 1/2 here. And it should be 1/2 root t projected on to the H2 axis, so that should be the projection onto this axis here. So in this way we draw the states, or the weights of the states. So we would then have mu1 here. mu2 has a minus sign for H1, but it's otherwise the same, so it must sit over here. And mu3 has 0 for H1, so it's projected on to here, and -1/3 for H2, so it's sitting down here. So here we have again drawn the states. We saw that before, but that was quite quick. And now we want to have a look at the step operators here. So let's see what the step operators do. Well, probably you don't recall the details, but we had a t operator that was pointing in this direction. We had a v operator. It was indeed at 60 degrees, pointing in that direction. And another operator, u, also at 60 degrees, pointing in that direction. So now this can be directly translated to this weight space. So we have then, for example, our t operator, t plus minus. It should take us in the horizontal direction. So it should take us from there to there. This should be the action of the t operator, of t plus. Similarly, t minus should point in the opposite direction, etc. So we should have v pointing here or there for v plus, and v minus in the other direction. We should have u pointing like this, or u minus in the other direction. These are our step operators. So now, knowing the position of this guy and the position of this guy, we can solve for t plus and t minus. So we can solve for the roots, the vectors. So this t plus, say, it took us from here to here. So it took mu2 to mu1, or mu1 to mu2. So the lattice point mu2 plus alpha 1 then must be equal to the lattice point for mu2. So this means that we can solve for alpha 1, for example. So if we have a look at what states we had, so we should have had, so from this we conclude that alpha 1 is mu1 minus mu2. So it is this state here minus this state here. So first we have 1/2 minus 1/2 minus minus 1/2. So it's 1, and then we have 1/2√3 minus 1/2√3. So this is 0. So we have that our alpha 1 is this guy. So this is then our root vector. So we found this root vector. And in the same way, by considering the action of v plus and u plus, one can find alpha 2 and alpha 3, so the other root vectors. And these are the root vectors. So the root vectors are the difference between the states. It's like the difference between different spin z and eigenvalues in the one-dimensional SU2 case. So we have these 3 root vectors. They are free, but we only have a 2-dimensional plane, so they are clearly linearly dependent. So we are, in a sense, carrying around too much information, bothering about all of them. So what we do then is that we choose 2 of them, and from this we can build. From this we have a linearly independent set, and such a set is called a set of simple roots, and from that everything can be built up. So actually we take as our independent vectors, we take alpha 2 and minus alpha 3. So alpha 2 we had from here, so that corresponded to v, so it's in the v direction. To be more specific, our e alpha 2 is here, And then we take minus alpha phi. So this is our alpha phi, and our minus alpha phi is pointing in this direction. So we take those two, and we want to build up the lattice of points in this space using the root vectors. Okay, so the lattice of points that one can have in this space is then given in relation to some starting point by taking an integer number of steps in the alpha 2 direction and an integer number of steps in the alpha 3 direction. So, for example, I can go from here to here using this vector, or I can go from here to there with a linear combination of this vector and this vector. So 1/2 this guy plus this guy should bring me there, etc. So I take 2 and I span my whole lattice points of states in this way. And so higher dimensional representations can be obtained in this way. To keep track of the different weights, that is the different eigenvalues of LZs and the analogs of the Cartan generators, one introduces the concept of a highest weight. The highest weight we define to be the state that has the highest eigenvalue for the first Cartan generator, and if there are many of those, has the highest value for the second Cartan generator. So, for example, we can see what the highest state is in for the SU3 multiplets here. So we want the one which has the highest weight for the first Cartan generator, and this is actually this guy because this is lower and this is lower, so we don't have to have a look at the second element to define that it's this guy. So this is then our highest weight state. And similarly, one can find the highest weight state for other representations, but I will not go into detail. And from those highest weight states, one can construct the other states. So let's say then that we start in this highest weight state, and then we can apply, in this case, minus alpha 2 and go in this direction, or we can apply plus alpha 3 and go in this direction. So the step operators take us between the points in general, a much larger point lattice here. I think this is where I want to end that discussion. Do we have any questions to it? Okay, so then I have a bit of time to talk about Young diagrams and Young tableaus. So if you have a look at this chapter 8, it's much more than I have time to cover in detail now. So I will be more wordy and I will not follow the notes particularly well. So first of all, what is a Young diagram? So a Young diagram is something like this, without labels, and that corresponds to a partition. So I will then have lambda 1 boxes here, lambda 2 boxes here, lambda 3 boxes here, and in the anomorph then. If I put in labelings in them, A, B, C, D, etc., then I have a Young tableau. And the point of the Young diagrams and tableaus is that they help us to construct the states, and they help us to take direct products of representations. So we had a look at the SU2 case and say that we had 3 states in a spin 1 representation, for example. And then if we took the product with another spin 1 representation, we draw the other one on top on top of all possible states, and then we projected down to some basic level, and we found a certain number of states. That was a bit more messy. That was a bit messy. Now, if we do it QCD, we can do the same thing. We have 2 dimensions. We can still draw it on the plane, and we can say that we start in some multiplet, a triplet, and then we can add to it, overlay on top of it another triplet, and then we can go to a number or an anti-triplet or whatever, and then we can go to a number of points in some sort of lattice space. That is already a bit messy for the 2-dimensional Catan sub-algebra case, and when you go to 3 dimensions, you run out of dimensions of your papers. You are probably not capable of doing it. So it's nice to have a better tool, and there is this better tool in the form of Young diagrams and Young tableaus, and they have to do with the symmetry of states. And I will not have time to go through exactly how this works. And even if I had more time, I would not do it, because the proof that the Young tableaus work in general is very complicated. So even if I went through all the material in these notes, which in this chapter, which I will not do, it wouldn't anyway not be completely satisfying. So instead, I will skip a lot and start with what I think is, in a sense, the principle of things. So what I have here is 2 Young tableaus. Sorry, diagrams, to be picky, because there are no labels, so it's just diagrams. And whenever I draw something, whenever I put the number of boxes horizontally, this means that I should symmetrize in states. Whenever I put boxes vertically, that means that I should anti-symmetrize in states. And symmetry and different states with different symmetries will be orthogonal, loosely speaking. So this is why this is useful. So let's start with having a look at the simplest case. So let's imagine that we have 2 possible quantum mechanical states. So we have 2 particles and we have 2 states. So we take then our Young diagram and we place our particles in the boxes 1 and 2, say. Then this is supposed to denote a symmetric state. So now let's have a look at what symmetric states we can have. We can have the case that particle 1 is in state alpha, and that particle 2 is also in the state alpha. So this is just another notation, alpha. So particle 1 is in the state alpha, particle 2 is in the state alpha, or by always writing particle 1 first and 2 later, we can drop the subscript 1 and 2 here. So the particles are then in state alpha alpha. This state is obviously symmetric with respect to changing position. So if I would change those alphas, if I would change the states, I would still have particle 1 being in alpha and still particle 2 being alpha. So it's obviously symmetric. I can construct another symmetric state though, even if the other particle, particle 2, is in the other state beta. So then instead of having, so then I can have particle 1 in state alpha and particle 2 in state beta. So I can have this. And this tableau here, or means that I should symmetrize with respect to the states. So I have here alpha 1, beta 2. Now I should symmetrize with respect to my particles here. So I have alpha 2, beta 1. So I swap the labels 2 and 1. Or going back to my default ordering, always writing the second state in second position, I would have beta alpha simply. This is clearly also symmetric. And in the same way, I can take beta with beta and have a symmetric state. So I can let both my particles be in the state beta. If I swap the two particles, obviously I have the same state. Now, thinking back to spin physics, if I add two spin halves, this actually corresponds to the total J equals to one state. So this corresponds to the triplet state. So J equals to one triplet. So what we did for SU2 was that we took the highest state, and in this case, that would be both spins up. Then we acted with the lowering operator, such that one spin at a time was turned down, and then we obtained this state. That state corresponds exactly to this state here. The symmetry, that is, the important observation is that the symmetry did not change under the operation of J minus. So we started in a symmetric state and we obtained a symmetric state. And then we could step further down with another J minus and obtain the states where both spins were down. But actually, the common property of all the states, regardless of the total spin Z in this J equals to one state, is that it's symmetric with respect to interchange of the two partons. This one can generalize, and I will take some steps towards showing how that can work in general. But before doing so, it could possibly be the case that someone wonders, well, why didn't I write alpha beta? Why didn't I write beta alpha? That should also be possible. That should certainly be possible, but it is the same as this state because I'm symmetrizing. So I do not need to consider that state. And if I did consider it, I would double count. And more generally, also if I have more particles and more possible states, I avoid double counting by requiring that the quantum numbers, so the label alpha and beta, do not decrease going from the left to the right. So like this. So let's say alpha is lower than beta, then it does not decrease. I have some order in between them. Okay, so thinking about this as a spin exercise, we have found the spin J equals to one state. So that was a symmetric state. Then there is also a spin zero state. And no surprise, this is obtained by antisymmetrizing. So now instead I put my particles on top of each other, so I denote that I should antisymmetrize. And then I say that my first particle is in state alpha and my second particle is in state beta, and I'm after the antisymmetric combination built up from this. So antisymmetrizing, so I will have that first particle is in alpha, second particle is in beta, but antisymmetrizing I get then that the second particle instead is in state alpha and the first particle is in state alpha. Or if I always write them in the same order, alpha beta minus beta alpha. So this corresponds to this state here. Here, we should note that we did not write alpha alpha or beta beta, and the reason for that is of course that then I would have alpha alpha minus alpha alpha, so that is 0. We cannot antisymmetrize in the same label, in the same state, then we will get 0. Get 0 with respect to interchange of the two particles. So from that we also get a rule in trying to find all possible states in the more general case, and that is that we can never have the same label in a column, never the same, never alpha alpha. That would not exclude the state beta alpha, but again, this would be excluded because it's not linearly independent compared to the state alpha beta. It's just minus that state, so that would also not count. And concluding those rules, we say that we always increase the label as we go down in the Young tableau. So in drawing a Young tableau, going from left to the right, the number cannot decrease. And going down, it must increase. So that's the two conclusions that we made so far. Okay, then we have, we complicate matters by considering a free particle state. So for example, a free electron state. Now we draw the Young tableau as 1, 2, 3, corresponding to free particles. Then we can have, so we have now 3 particles, but we still imagine that we only have 2 possible states. So we can have that all particles are in the same state. Then we can symmetrize, and that's easy. We can have the 2 particles are in the same state alpha, and the third one is in another state beta, and then we symmetrize that state. Or we can have that 1 is in alpha and 2 is in beta and symmetrize that state, or all particles can be in the same state. It's very hard to get a feeling for the whole document. So let's see, this I've spoken about. Yeah, this is where I was. So, okay. So the point here is that symmetrizing 3 particles, which are allowed to be in 2 different states. So for example, 2 different spin states, spin up and spin down, but in general, anything. We find a certain number of states, and we can calculate them. So it's 1, 2, 3, 4. And then what about antisymmetric states now with 3 particles? Well, if I only have 2 possible states for the individual particles, then whatever I do, I must write the same label twice in this Young tableau. And that would imply that I'm antisymmetrizing in equal states, and that does not work. So it is not possible with only 2 labels to antisymmetrize in 3 particles. I get 0. So that doesn't work. So in general, with only 2 states, one cannot have 3 boxes in a vertical column. Now with 3 particles, we can have something new. We can have mixed symmetries. So let's say that we start with 2 particles that are in a symmetric state. Then we can add the third particle. Well, if we add it here, we would have something that is symmetric in all states, but we could also add it down here. And that would imply that we first symmetrize in these states and then antisymmetrize in these states. Alternatively, we could start with having a state that is antisymmetric in 2, and then we add a third and symmetrize here. In both cases, we will have this sort of Young tableau. And in both cases, it would correspond to a doublet. So let's see, why does this correspond to a doublet? Well, it's a doublet because we can only have two states actually. So what states can we then have? Well, we cannot have alphas everywhere because then we would antisymmetrize in two equal states, so that would give us 0. What we can have is then alpha, alpha, they are allowed to be equal, but then we must have a beta here. Or we can have alpha, beta, beta. We wouldn't have a beta, alpha, beta, because that would be double counting in these two indices here. We call this reasymmetrizing, so this would be double counting in those. We would not have alpha, beta, alpha, because here we would have the same label, and it's supposed to be antisymmetric, so that does not work. So hence, we have only two states, so hence that would correspond to a doublet. So what we can do though is that we can place the particles in different positions here. So we can have 1, 2, 3 or 1, 3, 2. And placing them in these two different ways, 1, 2, 3, 1, 3, 2, we can build up different wave functions. So we can build up the wave function where corresponding to this state. So first we have alpha 1 and alpha 2, sorry, particle 1 and particle 2 in the state alpha. And the third particle in the state beta. This state is in itself obviously symmetric with respect to changing those two labels, this one and this one. So doing the symmetrization amounts to doing nothing. Then we add a beta here, but then we should antisymmetrize in this beta and in this first alpha here. So I have another state where this guy and this guy has rather this state and this state have swapped place. Then I could have, so here I started with having my states 1 and 2 horizontally. I could also start with having the antisymmetric state in 2 and 3. And then, sorry, in 1 and 2, and then adding on my third state over here. And I would play the same game. And all that would happen would be that the relative position of 2 and 3 change. So I would always swap place of the second and the third guy here. So for example, this guy would got those would swap place and etc. The states obtained in this way are actually not necessarily orthogonal, but they are linearly independent. So this directly works for counting degrees of freedom, but it does not directly work for writing down the states. So if one would actually want to write down states, one may have to make them linearly independent. But I will not go into that in detail. Do we have any questions? Okay, so now let's see what happens if we instead have 3 possible states. So this is the case in QCD. In QCD, we would have 3 colors, say red, green, and blue, but we can also imagine the 3 labels being anything of which we have 3, so 3 possible states. Then if we have only 1 particle, how many states do we have? Well, we have 3 possibilities for the 3 different labels, alpha, beta, and gamma. So we have 3 states. Now, if we have, now we can construct antisymmetric combinations, having 2 of them, or antisymmetric combinations, in this case also having 3 of them, since we have 3 different labels. If we have three different labels and we want to construct something that is antisymmetric, I must have a different label up here and down there. So I cannot have the same, so I can then get a total of 3 different states because there are 3 different ways in which I can exclude one label. So they're always different, that is, there is always 1 out of 3 that does not appear, and that 1 can be chosen in 3 different ways. So I have a 3-dimensional representation. So this corresponds to my anti-quark representation in QCD, and there are 3 of those, and they can actually be seen as antisymmetrized versions of the quark states. Then if I have, then I can construct symmetric states. So I can count how many symmetric states I have. So I have, for example, alpha alpha, alpha beta, alpha gamma. There was all my states with 1 alpha, then with 1 beta. I don't count this one, it's already counted, so that would be beta alpha, but one I don't count, so I have beta beta, and I have beta gamma, and finally I have 1 state without beta, so that is gamma gamma. So counting those, I have 6 states. Similarly, I can symmetrize in 3 different, I can symmetrize 3 different particles that are allowed to have 3 different states. So that amounts to all ways of inserting labels such that my label is always increasing when I go that way. So you can easily convince yourself that it's these states, and so there are 10 of them. And I can have finally mixed states. And one can again count the degrees of freedom according to the rules and find out that there are 8 of those. These different states can also be, plotted in the weight diagrams that we have seen. So, for example, I can have both particles having these weights, and I would then I could then draw that as a point in this weight diagram, etc. But let's not do that, because I rather want to move on to the real use of the Young tableaus. And the point is that they are very handy for constructing direct product representations. So let's see. First, before doing that, I should point out that given a Young tableau, one can calculate the dimension of the representation. And this is a case where the proof is complicated, so I just state the result. So the dimension of the representation, assuming that we have n different states, it is given by a numerator divided by a denominator. The numerator is obtained by placing in this box n. In the next box, when I go to the right, I increase the number with 1. So I have then n plus 1, and then I increase again, so I have n plus 2. When I go down, I decrease with 1. So I have n minus 1, and n minus 2. This gives me my numerator. But then I should divide with the denominator. And the denominator is given by the so-called hook length. The hook length is the length of a hook going horizontally and vertically through the box in question. So here the hook length is 3, for example, because I encounter 1, 2, 3 boxes, and here the hook length is 1 because I only encounter 1 box. So in this way, the dimension can be calculated. So I think this is easiest to see in a single example. So let's take a look at the dimension of this. We actually may recognize this so before that it was the octet. So let's see if this is what we get. So first in the denominator, I start with 3. I increase with 1 going this way. So I have going horizontally, and going vertically down, I decrease with 1. So I have 3 times 4 over 2. And then I divide it with my hook length. So the hook length of this box here is 3. The hook length of this is 1, and the hook length of this is 1. So I have then for my dimension 3 times 4 times 2, that's my numerator, over 3 times 1. There's a typo clearly here. This must be a 3. 3 times 1 times 1, and now crossing out the 3's, that is 8. So in this way, the dimensions can always be calculated. Yeah, and now I have just a few minutes to come to the real benefit of the Young tableaus. So the real benefit is in finding the direct product representations. So now imagine that I have 2 representations. They are both depicted by some Young diagrams. And I want to take the direct product. Now there is an easy way of doing that. That is, take the first one. To that, we want to add the second one somehow. In the second one, we write A's everywhere in the first row. We write B's in the second, and we write C's in the third. Now the rule is, and what we do then is that we take these labels and attach them to this diagram somehow, but according to certain rules. So we are doing it one label at a time, and we are doing it such that no 2 squares with the same label should occur in the same column. So this is because of the antisymmetry. Also, the total number of A's counting from the right to the left, and then going down and counting from the right to the left, and then go down to the next row and counting from the right to the left, cannot be less than the number of B's, which cannot be less than the number of C's, etc. at any point in the creation of this new Young tableau. Also, if we have the same Young tableau appearing more than once, we cross it out. So if the labels are the same, we cross it out, but if the labels are different, we keep it. Okay, so let's have a very quick look at how this goes in SU3. So let's say that we have this particular Young tableau, and we want to multiply it with the octet. So we make labels here A, A, B. Then we add to this basic diagram A's in all possible places. First A, and then after that I add to each of these a second A in all possible ways. So for the first one, for example, starting with this guy, I add a second A there, and there, and there. Here I antisymmetrize in 3 labels, and there's only one way of antisymmetrizing in only 3 different labels, and since there's only one way that corresponds to a singlet, and this means that I can cross this column out. Then I remove possible instances of these being the same, and by the same rule I attach B's everywhere, and I cross out all the cases where I have identical diagrams, and I cross out all columns which are 3 long, and then I remove all the labels, and I'm finally left with a set of diagrams like this. And from these I can calculate the dimensions by the hook rule. And actually this is a very nice topic for an exam question, so probably maybe I will not ask it because we did have so little time for it. But it's a very efficient rule of finding representations, and I'm fully aware that it was not possible to follow any details in what I did just now. I hope that you got the main idea that symmetrizations can be used in finding different states, and that there's a powerful tool called Young laws or Young diagrams for finding all different direct direct sum state in the direct product of two different representations. Okay, and now it's 12 o'clock, so it's time to stop, and you are welcome to ask questions. But I take that as we again have no questions. So then I say thanks for today, and the last session of the course will be the exercise class for tomorrow. The intention was the groups were supposed to solve the problems. If you did not manage, it would be appreciated if you could email me in advance that your group didn't manage. And I don't mean half an hour before the start of the session, but a bit longer in advance. Okay.
I have a question about like study questions for the world.
Sorry?
Like study questions for the world. Do we have any of those? Like we
study questions for the oral exams. No, I have no study questions for the oral exams. It's like for the written exams. All material is covered.
Okay.
I know, I'm fully aware that students often get this list in basic courses, but I think that at this level you should be quite capable of judging what is important and what is not so important.
Okay.
So I focus more on the concept and the principle, and I will not squeeze you on factors of 2 and details. Sometimes when these lists are provided, the result is also that students are upset if one is asking something that is not in the list. But the exam is supposed to be on the whole course. And if I confine myself to a list, I cannot probe the whole content of the course, which is supposed to be the meaning of the exam. So personally, I don't like this sort of lists so much. And I think that at this level, you're quite capable of selecting material as well. It's a bit different when you're a first-year student. Okay, maybe there are some more questions regarding the exam or anything. Okay, if not, I say thanks for today. I stay here for 1 or 2 more minutes to see if someone has some smaller questions. So there are a few people still left. Do we have any questions? Okay, so I assume that there are no more questions, and so I say thanks for today.